This episode is brought to you by Brilliant. On almost every powered vehicle, the brake system produces more deceleration force than the drivetrain's acceleration force. Formula One race cars are an extreme example of this and can produce up to 6 Gs of braking force while maxing out at around 2 Gs of acceleration. In fact, when compared to most vehicle drivetrains, their brake system has, by far, a much larger capacity for power transfer. Even a mundane small compact car will dissipate over 0.12 kilowatt hours of energy during an emergency stop from 100 kilometers an hour or about 60 miles an hour. This one braking event that occurs over a few seconds dissipates enough energy to fully charge around 10 completely drained iPhone batteries. Fundamentally, a brake is simply a mechanical device that inhibits motion. However, in its contemporary form, the brakes found on today's road vehicles are highly engineered systems that can sustain repeatedly converting large amounts of kinetic energy into thermal energy while remaining both durable and reliable. For the vast majority of vehicles, these systems work by engaging friction surfaces that are coupled to rotating axles or wheels to dissipate kinetic energy. The first wheeled vehicle brake systems consisted simply of a block of wood and a lever mechanism. To stop a vehicle, the lever was pulled, forcing the block of wood to grind against the steel rim of the wheel. Wooden brakes were commonly used on horse-drawn carriages and would even be used on early steam-powered cars that were effectively steam-powered carriages. While they were effective for the low speeds of these vehicles, they would quickly approach their limits when used in higher energy applications, such as in cable cars. Cable cars use pine blocks situated between the wheels that are pressed into the track when actuated by a lever. While cable cars typically operate at speeds below 10 miles per hour, the sheer mass of the car would wear down these supplemental wooden brakes in just 3 days of use and often produce smoke while being used. In 1888, Benz introduced the first gasoline car fitted with a metal wheel that was covered with an air-filled rubber tube. This was the precursor to the pneumatic tire, and shortly thereafter, fully rubber pneumatic tires would grow to dominate the budding automotive industry. With this, the wooden block brake system became obsolete. The first brake system specifically designed for cars with pneumatic tires would be developed from an idea first devised by Gottlieb Daimler. Daimler's system worked by wrapping a cable around a drum coupled to a car's wheel. As the cable was tightened, the wheel would be slowed down by friction. A few years later, French industrialist Louis Renault would patent the concept in 1902 as the drum brake. Renault's drum brake design employed a flexible steel band lined with woven asbestos that wrapped around the steel drum. The band would be actuated mechanically so that it tightened around the drum, slowing the wheel. While it was far more responsive than a wooden block, the exposed friction material of the external design made it less effective when exposed to the elements. As dirt and water became trapped between the friction lining and the drum, the braking effect would be drastically reduced. A few years later, this vulnerability would be resolved with the development of the internal shoe drum brake. These systems similarly used a steel drum that was coupled to the wheel. However, within the drum was a fixed plate where 2 friction shoes are mounted. These shoes were typically made of 2 welded steel pieces called a web and a lining table. The lining table formed a surface for which a friction material was either riveted or attached with an adhesive, while the crescent-shaped web contained the holes and slots needed for mounting hardware and return springs. These early systems used a mechanical cam that, when rotated, would apply a force through the web to the lining table and its friction material. As this force expands the shoe outwards against the inner wall of the drum, the rotational energy of the wheel is converted to heat, slowing it down. On drum brakes, the shoe located towards the front of the vehicle is known as the primary shoe, while the rearward one is designated the secondary shoe. While in many applications both shoes are interchangeable, their positioning of the friction material lining relative to the drum is determined by their designation. The friction lining material used on brake shoes need to be resistant to high heat and wear, as well as be unaffected by environmental factors such as temperature and humidity. They must also possess a high coefficient of friction, creating a friction force of around 40% that of the clamping force. While chrysotile asbestos remained the primary component in brake lining friction material, Formulations were developed that resist brake fade from heat buildup and overall improved wear characteristics. These friction compounds used a combination of graphite, various powdered metals such as lead, zinc, brass, and aluminum, and were typically bound with a phenyl formaldehyde resin. While drum brakes offered superior braking response and durability when compared to previous systems, the mechanical actuation of brakes was quickly becoming a limiting factor in increasing braking forces as vehicles became heavier and faster. Mechanical braking mechanisms also had more points of wear, were more difficult to package into vehicles, and required regular adjustments to compensate for shoe wear. In 1917, aviation engineer Malcolm Lockheed was granted a patent for an idea that overcame the limitation of mechanical brakes by using hydraulics. From this, he founded the Lockheed Hydraulic Brake Company in 1919, where he further developed the concept, acquiring more patents along the way. Hydraulic brakes operate on the principle that when a force is applied at one point of a hydraulic system, it is transmitted to another point by means of an incompressible fluid. This force can be multiplied by varying the sizes of the pistons at each end of the system in a manner similar to a mechanical lever. In hydraulic brakes, a smaller piston that travels a relatively longer distance is used to transmit a force through fluid displacement to a larger piston with less travel that directly pushes on the brake shoes, multiplying the force applied in the process. On a vehicle, the smaller piston is housed in an assembly known as a master cylinder. The master cylinder also contains a reservoir that holds a reserve capacity of hydraulic fluid as the volume of fluid within the system fluctuates with use. This excess fluid also keeps air from being aspirated into the system. A brake pedal or lever is connected via a pushrod to the piston, where force is applied into the system. A return spring within this cylinder returns the piston when that force is removed. As the piston is pushed down the bore of the master cylinder, cup seals that seal fluid in the pressure chamber cause a buildup in pressure as the seal moves past the vent. A replenishing port that is located next to the vent port allows fluid to flow back into the low pressure side of the piston, preventing a buildup of vacuum pressure behind the piston that could resist the piston as it travels down the cylinder. When the brake is released and the piston retracted, the displaced fluid returns to the reservoir. At the drum brake, a hydraulic cylinder containing two pistons replaces the cam mechanism, applying a force outwards on the brake shoes as pressure builds within the system. A set of retracting springs on the brake shoes restore their position when the brakes are released and pressure is reduced from within the brake cylinder. In hydraulic brake systems, a combination of rigid hydraulic lines made from either steel or a nickel-copper alloy and flexible reinforced rubber hoses are used to transfer fluid pressure between the master cylinder and the brake cylinders. These small, malleable brake lines could now be easily routed through the chassis of a vehicle in hydraulic circuits, with the only failure points being the line's structural integrity and the fittings that join them. Hydraulics also increased safety through redundancy by allowing the brake system to split into two independent circuits using tandem master cylinders. On most cars, these circuits are either split between front and rear wheels or diagonally. This redundancy prevents total brake failure as each circuit is hydraulically isolated from the other. Maintenance when compared to mechanical brakes is also dramatically reduced as only service of the hydraulic fluid is needed. Air must also be bled from the system if it is disassembled, as air is compressible and can prevent fluid displacement when trapped between the working fluid. Because the hydraulic system can maintain the same force throughout the brake cylinder's entire travel distance, a ratcheting mechanism would eventually be developed for drum brakes that moves the shoe outwards as they wore, eliminating the need for adjustment. This automatic adjuster would help keep a consistent feel in the brake pedal or lever as the friction material wore thinner. Four-wheel hydraulic brakes would first appear on a production car with the 1921 Duesenberg Model A, though Rickenbacker would be the first manufacturer to offer them on vehicles that were mid-priced and more mass-appealing in 1922. Shortly thereafter, other manufacturers would adopt hydraulic brakes and it quickly became standard. The concept for a mechanism that multiplies the force of braking using external power has existed since the early 1900s. Many of these ideas involve using compressors to pressurize either air or hydraulic fluid in order to reduce the force needed by an operator to actuate a vehicle's brakes. In the late 1920s, Bendix inventor Victor Clearath, in collaboration with race car driver Caleb Bragg, would develop a novel approach to boosting brake power using engine vacuum. First introduced by the Pierce Arrow Motor Company in 1928, this system, originally designed for aviation, uses the vacuum generated by an engine's air aspiration to build a vacuum within a device known as a brake vacuum servo. When the brake pedal is pushed in, one side of a diaphragm that divides the servo is exposed to the atmosphere through a valve. This creates a pressure differential on the diaphragm that develops enough force into the master cylinder's pushrod that it boosts the operator's braking effort. When the brake pedal is released, a return spring resets the diaphragm's position, closing off the air valve and returning the entire servo to a full vacuum condition. By the 1930s, vacuum-assisted drum brakes began to grow in popularity and could be found fitted into Cadillacs, Lincolns, Mercedes, Duesenbergs, and Stutz cars, though alternative brake boosting systems were still pursued. One notable example is GM's HydroBoost system. First introduced in the 1940s, HydroBoost uses hydraulic fluid to transfer power generated by the vehicle's steering pump to aid in the force applied to the master cylinder. However, vacuum-boosted brakes are by far the most popular type of assisted brakes due to its simplicity and reliability. The next leap in braking technology got its start in England in the late 1890s with the development of a disc-type braking system by the Lanchester Motor Company. The system used a cable-operated clamping device called a caliper that would grab a thin copper disc that was coupled to the wheel in order to slow its rotation. The system proved to be impractical, though the concept would resurface during World War II, where it would be adopted to aircraft and tanks. This was facilitated primarily by advances in hydraulics and metallurgy, and by 1949, the first four-wheeled hydraulic disc brake system adapted from aviation would appear on cars made by compact car manufacturer Crossley. However, the system proved to be problematic as the aircraft calipers used could not hold up to the repeated use of driving. The adoption of production car disc brakes was mostly shelved by the industry as further development was still needed. In the mid-1950s, disc brakes began to demonstrate their superiority in racing, with the 1953 24 Hours of Le Mans winning Jaguar team using the technology on their race car. Compared to drum brakes, disc brakes offer better stopping performance because of the disc's exposure to open air. This allowed for dramatically better cooling, making them less prone to the brake fade caused by brake components overheating. Their simpler action also provides better feedback through the brake pedal. They are also self-cleaning by design, making them resistant to contamination and exposure to water. By 1955, Citroën would introduce the Citroën DS, the first true mass-production car to field disc brakes. For the vast majority of modern disc brake systems, the disc or rotor is made from gray cast iron. This durable yet inexpensive component is generally sandwiched between the wheel and its hub assembly, though in some applications it can be mounted inboard just before the drive axles to reduce unsprung weight. The rotor slots through the brake caliper, which is mounted to a stationary bracket. The caliper houses one or more steel hydraulic pistons that, when pressurized, apply a force to a pair of consumable friction material inserts known as brake pads. This force drives the brake pads into the rotor, converting the rotational energy of the rotor into heat through friction, which is subsequently dissipated by the rotor. Brake calipers are designed to be either floating or fixed. A floating caliper or sliding caliper moves parallel with the rotor on slide pins as it rotates. They only contain one piston on the inner side that pushes the inner brake pad until it makes contact with the rotor. As the piston continues to expand, it pulls the caliper body with the outer brake pad closer to the rotor so that both pads are now applying pressure evenly to both sides. While the slide pin sticking from dirt or corrosion is a common failure point on floating calipers, they are cheap to produce and are the most common type found on vehicles. A fixed caliper, by comparison, does not move relative to the disc and can have multiple pistons on each side of the disc, allowing for a larger contact point with the rotor as well as greater braking force. However, they tend to be more complex and expensive to produce and are generally reserved for heavier vehicles or performance applications. Within both types of brake calipers, the pistons are sealed using a square cross-sectioned fluid seal. This results in a resistance to the piston retracting due to seal twist. This resistance causes the brake pads to always remain in close proximity to the rotor after its last expansion, effectively forming a self-adjusting mechanism for brake pad wear. Over the next 2 decades, disc brakes grew in popularity, and by the 1970s, front disc brakes became common on most new vehicles, though drum brakes were still popular for rear brakes due to their lower cost and the need for less rear stopping power. Drum brakes are also more easily adapted for pneumatic operation and still remain a popular system for tractor-trailers and other air-powered braking vehicles. Starting in the mid-1950s onward, initiatives were made to standardize and regulate the composition of critical brake components, with most of these specifications being developed by the International Standards Organization, the Society of Automotive Engineers, and the United States Department of Transportation. These specifications cover critical elements such as the composition and performance of the hydraulic fluids used, the composition of brake friction materials, the size and materials for hydraulic lines, and even the metallurgy of brake rotors and drums. From these regulatory bodies came the emergence of a baseline expectation for braking effectiveness, safety, reliability, and serviceability that could be found in every vehicle manufactured. For the first half of the 20th century, techniques to enhance braking in extreme conditions have been experimented with. Most of these systems focused on heavier vehicles such as trains and aircraft. Mechanical anti-skid systems for aircraft landing gear brakes in particular were of high interest during World War II. These systems attempt to modulate brake pressure to find the optimal amount of braking force that a tire can dynamically handle, just as they begin to slip. In most situations, maximum braking force occurs when there is around 10 to 20% slippage between the braked tire's rotational speed and its contact surface. As more slippage occurs, the rolling grip of the tires diminishes rapidly, and sliding friction becomes a greater proportion of the force that slows the vehicle. This sliding friction causes excessive local heating and melting of the tires, while providing very little friction with the contact surface, dramatically increasing stopping distance. At this point, steering also becomes ineffective since the grip of the tire is entirely consumed in braking the vehicle. By the early 1950s, the first widely used anti-skid braking system called Maxrit would be introduced by Dunlop. This purely mechanical system used a flywheel to detect the rapid wheel deceleration caused by skidding in order to trigger a brake modulation valve. Maxrit quickly became popular in the aviation world after testing found a 30% reduction in stopping distances in aircraft. However, the system lacked the lower speed response needed for road vehicle use. It would take the integration of electronics into braking to make the concept viable for cars. Once again, aviation would pioneer this leap in braking technology, with the first fully electronic anti-skid braking system being developed in the late 1960s for the Concorde. By 1969, Ford introduced the first production electronic anti-skid system for a road vehicle called SureTrack as an option. The next year, both GM and Denso also started developing their own systems. All three manufacturers derived their designs from developments made by Fiat engineer Mario Palazetti. Palazetti's research and patents would eventually be acquired by Bosch, where the name ABS or anti-lock braking system would be coined. In general, an ABS system consists of an electronic control unit, wheel rotation speed sensors, a hydraulic unit, and a hydraulic pump. The controller, which continuously monitors the wheel rotation speed sensors, is specifically looking for abnormal rotational deceleration in one or more wheels. Under extreme braking or in slippery conditions, just before a wheel locks up, it will experience a rapid rotational deceleration. Left unchecked, a complete stop of the wheel rotation can occur in under a second. Because such a rapid deceleration is impossible, the controller reduces brake pressure to the offending wheel using electronically actuated valves within the hydraulic unit. As the wheel's rotation starts to accelerate as it transitions out of braking, the controller rapidly increases hydraulic pressure to the wheel once again until it sees the deceleration again. This reserve pressure is created using a hydraulic pump in conjunction with an internal hydraulic accumulator. The entire process of cyclically releasing and repressurizing the brake occurs rapidly at up to 15 times a second. This in effect prevents the tire from significantly changing rotational speed outside of its braking deceleration envelope. Because the tires are always kept at the edge of locking up, the system provides the maximum braking power possible. The first ABS system only had one valve, which controlled both rear wheels, and one wheel speed sensor located in the rear axle. This is known as a one-channel system. By the mid-1970s, three-channel systems that finally brought ABS to the front wheels began to appear. These systems had a speed sensor and a valve for each of the front wheels, while still retaining only one valve and one sensor for both rear wheels. Within a decade, full 4-channel ABS systems that could individually sense and valve each wheel independently became common. The electronic units of ABS systems would also grow in complexity alongside the embedded microprocessor industry to bring even more sophistication to these systems. With the ability to now monitor each wheel's rotational speed thousands of times a second and apply individual wheel braking in millisecond bursts, electronic stability control would soon be incorporated into ABS systems in the late 1980s and 1990s. Electronic stability control systems use additional sensors that monitor the vehicle's dynamics, such as a steering wheel angle sensor and a gyroscopic sensor, to brake individual wheels so that in disruptive conditions, or even in normal cornering, the vehicle remains on a predictable trajectory. More advanced systems can even implement a traction control system that can both pulse the brakes of individual wheels to route power as needed, and even control the engine's throttle input directly. With the introduction of tire pressure monitoring in the mid-2000s, the ABS systems of many vehicles would even be tasked with detecting the underinflation of individual tires by sensing their minute differences in rotational speed. Today, four-wheeled disc brakes with ABS and electronic stability control has become standard for most vehicles. The materials used to create brake pads have also long evolved past hazardous asbestos to organic-based friction materials made from cellulose, fiberglass, rubber, and even Kevlar. These softer, quieter, but faster-wearing pads offer the best compromise between performance and comfort for the vast majority of vehicles. More aggressive semi-metallic pads can contain up to 60% steel and copper also exist for performance applications, though at the cost of noise and rotor wear. Beyond metallic pads are ceramic pads that are composed of clay and porcelain bonded to copper flakes and filaments. These tend to offer the durability of metal-based pads while having far less noise and wear characteristics when at operating temperatures. In the late 1970s, the use of reinforced carbon as a braking material had begun to migrate from the aviation world to racing, with carbon-carbon braking quickly becoming used in most top-level motorsports worldwide. Carbon-carbon brakes are made of a composite material consisting of carbon fiber reinforced in a matrix of graphite. They offer unprecedented levels of frictional performance and improved structural properties at high temperatures when compared to cast iron. However, they do need to reach a very high operating temperature before becoming truly effective, and are not well suited to road use. Around the early 2000s, a derivative material known as carbon fiber reinforced silicon carbide would start appearing in high-end sports cars. Called carbon ceramic brakes, they carry over most of the properties of carbon-carbon brakes while being both more dense and durable, and they possess the key property of being effective even at the lower temperatures of road car use. Starting around the mid-2000s, one of the most dramatic changes to how we slow a vehicle down would start to emerge, though not from the technologies involved in braking, but rather the vehicle's power plant. The inclusion of an electric motor into a vehicle's drivetrain, whether via hybrids or full electric designs, bring with it the concept of regenerative braking. Regenerative braking uses the electric motor as a generator to convert the vehicle's kinetic energy back into electricity, which is then used to recharge the onboard battery. While braking through the drivetrain has been around since the advent of the internal combustion engine, electric drivetrains can recapture this energy so aggressively that in its contemporary form, up to 10 times less load is placed on the braking system when compared to similar vehicles with an internal combustion engine. This reduction of load dramatically reduces the consumables within the braking system, with brake pads easily aging out far before actually wearing out. When combined with the integration of brake-by-wire systems, regenerative braking is also changing the way in which we decelerate a vehicle. With the advent of one-pedal driving and even hand controls to throttle the amount of regenerative braking effect, the current transition to fully electric vehicles will truly bring around new ways to reinvent stopping the wheel. The split-second computations needed for ABS and stability control is really about managing uncertainty. Modern safety systems are essentially high-speed decision-making machines, constantly weighing the likelihood of unwanted vehicle dynamics from a mix of sensor data. If you want to build the kind of intuition that lets you understand how to analyze variables and predict outcomes like an engineer, you should check out Brilliant. Brilliant is an incredible way to master math, computer science, and engineering because it focuses on helping you truly understand the concepts rather than just memorizing them. It's built on the belief that you are already a problem solver. You just need the right tools to unlock that potential. Instead of sitting through long, passive lectures, you learn through interactive, hands-on challenges that guide you to those satisfying aha moments. They've also rolled out massive updates, doubling the size of their content library and adding personalized practice sets that adapt to your progress, ensuring you are always being challenged at exactly the right level. You'll also be confident that you're learning the right way because Brilliant is handcrafted by an award-winning team of teachers, researchers, and professionals from MIT, Harvard, Google, and more, harnessing that expertise to design personalized practice sets just for you. And speaking of analyzing outcomes, a fascinating starting point I highly recommend is Brilliant's Probability and Chance course. It teaches you how to use probability to make better decisions from uncertain data. This is a critical skill whether you're designing a safety system or just navigating the uncertainties of daily life. With the new year coming up, a lot of us are thinking about self-improvement, and building a strong daily learning habit is a great way to kick off that journey. To start reaching your serious learning goals, go to brilliant.org/newmind or scan the QR code on the screen. That link will let you learn for free on Brilliant for a full 30 days. Brilliant is also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything they have to offer.